This is session 6 for Models in Epidemiology and Biostatistics. I'm Gordon Hilton-Fick, and we're now going to look at, in considerably more detail, issues of modification and confounding. And we're going to be dealing with the circumstance in which for the sake of discussion, we'll have men and women, we'll have young and old, but we'll also have them, the person's actual age, and we're prepared to assume that the relationship between the log of odds and disease is a line, a series of lines, and we'll see that in a minute. Now, there's an argument then that we would have a model with all 8 of the terms that are displayed there. Well, as I noted in, I think it was session 3, the comparable model with age group rather than actual age, if we were to consider all 8 terms, there are in fact some, 256 possible models that one could consider with various subsets of these 8 regression coefficients being in the model. Now, there are 2 exploratory methods that are often noted in situations where we have quite a number of models to consider. There is so-called stepwise regression, and there is so-called best subset regression. Both have been implemented in most software systems. And as I would note that, both of these methods would be viewed as highly exploratory. It doesn't mean you couldn't just have a look and see what they say, but none of the science is really implemented, directly at least, in either stepwise or best subset methods. Further, we want to have models for which we can see the epidemiology. Now, it may be that the epidemiologic issues will start getting more and more complicated, but at least it isn't just a model that appears to fit well, and that's its merit, not exactly what it is that this model might be attempting to do in terms of understanding the epidemiology. So with that background, let's take a look then at the circumstance in which we have possibly 4 lines. Okay. We've got a line for the unexposed women, we've got a line for the unexposed men, a line for the exposed women, and a line for the exposed men. And it should be, I think, fairly clear here that if we were to start our investigation of this admittedly pretty complicated situation, starting with this model with all 8 terms gives us the 4 lines that I have displayed there in terms of their equations. There are a number of situations that one might see with such an investigation. And what I thought I would do is take some time to go through visually with one of the scenarios that can be seen and is indeed seen from time to time. And that will be seen with the first illustration that I'm showing you here. So here we've got a hypothetical, admittedly, but a circumstance in which we have On the vertical scale, the log odds of disease. And on the horizontal scale, we have age. Now, this looks pretty complicated, but let's see if we cannot gain some appreciation for what's going on here. Let's first look at the men. The men are displayed here with two lines. The men subject to exposure and the men who are not subject to the exposure. And we have a yellow line with this display for the exposed men and a red line for the unexposed men. And remember, the vertical scale here is the log of the odds of disease. What does that mean? Well, we saw in session 5 that it is the vertical distance between those two lines for any age that gives us the log of the odds ratio. Okay. So let's have a look, for example, at the 30-year-olds that are in this study. What we can see is a vertical distance that runs from about here to about here. We can see that distance. Let's now look at the same vertical distance for the 50-year-old males. Now we see we have this number compared to this number. This distance is this difference, or this distance here. And notice, by exploring what's happening with the 30-year-olds and the 50-year-olds, we can see that the vertical distance is increasing with age. What is that saying? It's saying the log of the odds ratio for the men is increasing with their age. Okay, so the log of the odds ratio, meaning that the issue of association between disease and exposure is increasing in its magnitude for the older men. Hope you can see that. Because now what I'd like to do is take a look at the women in this study. Let's now first consider the green line, which is the women that were subject to the exposure, and the women who are not. The green line minus the blue line gives us the vertical distance. The vertical distance is the log of the odds ratio. So we can see for 30-year-old women, we have a distance that's like this. Okay. But for 50-year-old women, the vertical distance is now this. And so now we can see that the log of the odds ratio for 30-year-old women is higher than the log of the odds ratio for 50-year-old women. What is that saying? That's saying that the log of the odds ratio decreases with age for the women. All right, now we've got two things going on here. We've got that for the men, the log of the odds ratio increases with age. Well, notice that that's saying that for the men, age is a modifier. And the form of the modification is that the log of the odds ratio increases with age. So we have that not only is age modifying for the men, but it's doing so in a rather specialized way, in a way that we can see visually then, that the odds ratio is increasing with age. But for the women, we get the opposite. We get that the log of the odds ratio is declining with age. So we can see that for the women, we can see that with this visual, that age modifies. But it's doing so in a different way. The modification form is that the log of the odds ratio for the women declines with age. My. What's that saying? Well, that's saying that the odds ratio shows two different patterns, one for the males and one for the females. So what can we see? We can see that age modifies, but the form of the modification is different for the men and the women. In other words, age modification depends on gender. Or if you like, and we're reusing the same word again, but we're saying that age modification is modified by gender. That's maybe an overuse of one word. The fact that we need to say how there is age modification. And we can see that its form is one of rising odds ratios for the men, rising with age, but declining odds ratios for the women. Okay. So that's summarized in this text that I've just included here. Notice that the exponent of that difference, of that vertical distance, is the age-specific odds ratio, either for the men or for the women, and we saw that last time. It's age-specific because we have actual age measured, and we can contemplate, at least conceptually, the age-specific odds ratio for any particular age for any particular group, either the males or the females. Okay. So what does that mean? The log of the odds ratio rises with age for the males and declines with age for the females. That is also, now, the vertical scale here, just to be clear, the vertical scale here is the log of the odds ratio now, and this is age. Notice we get two equations, and both of them are lines again, aren't they? We see that the log of the odds ratio is a line for the women, and the log of the odds ratio is a line for the men. Now we can look at those two lines and notice, because visually there, the lines have different slopes. How can that be? Well, we can see that for the women, the line has a negative slope. Right? It's a negative, it's declining. So that says that beta 6 here would be negative. Now the slope for the men is positive, but it's the form of the slope from this model is captured by beta 6 plus beta 7. In other words here, beta 7 is big. It's positive and it's large, larger than beta 6, so that we get a positive slope for the men. The log odds ratio increases with age, and the log for the men, and the log odds ratio decreases with age for the women. Right. There's the equation. There's the visual. All right. One more visual then. How about we take the difference between the men and the women? Okay. So now this is the difference between the log odds ratio for the men and the log odds ratio for the women. And what do we get? We get something that is a line again with a positive slope. And what's the slope? It's beta 7. Oh yeah. So all of this is giving us the circumstance in which the log of the ratio of odds ratios is a line, if this model is at all appropriate. And the slope of a line is telling us about whether or not age modification depends on gender or gender modification depends on age. Now, this is the same circumstance that we saw when we just had age groups. But now we've got lines. Okay? We've got 4 lines displaying the log odds of disease. 2 lines for the log odds ratio, and 1 line for the difference between the 2 log odds ratios. Now, this visual these equations that I'm showing you are implications from the model we started with, from this model that we started with, this one. Right. However, these visuals are very specific to this illustration. So there's lots of other scenarios we might see. But one thing that I want you to keep in your mind for the moment is that beta 7 is not 0. And that's telling us that the ratio of the 2 odds ratios depends on age. And that gender modification depends on age. Or symmetrically, that age modification depends on gender. Okay, now, we started this display by beginning with this model here, with all 8 terms. But there's something that we need to now begin to explore. In fact, if the issue is really about the study of the 2 lines in the log odds ratio, or the line in the difference between the 2 log odds ratios, then in fact there are 8 models that one could conceptualize as being possible to describe the issues that are implicit in this work. Now, notice then that we are beginning to see, there's several possible models that could be in play here. Now, it is true that number 1, the first one listed there, might be the one we need. And it perhaps is the most widely seen and the most widely considered. But it turns out that any one of the others is at least possible. Now, let's take a look at one example just to give some context here. Notice that the expressions beta 1, beta 2, and beta 3 all involve statements about the log odds of disease in the absence of exposure. Let me just clarify that for you, because if exposure is 0, if we're thinking about individuals who are not exposed, then E is 0, and if that's the case, then all of these terms, beta 4, beta 5, beta 6, and beta 7 are all 0. Right? So we can see then that beta 1, beta 2, and beta 3 are describing possible circumstances for the unexposed in the study. Many possible situations. Sometimes they pop up, though. Let's look at one situation, and that is model number 4 that I've listed here. Okay. So what do we got with model 4? The term beta 3 is is set to 0. What is that saying? For the unexposed, we have two parallel lines. One line for the unexposed males and one line for the unexposed females. Okay? Notice with equation 4, with E equals 0, meaning unexposed, we simply get two parallel lines. The term beta 3 is enabling the fact that it is possible that in model 1, for example, that the two lines for the unexposed are possibly not parallel. However, with model number 4, there's an assumption of parallelism among the unexposed. Well, this turned out to come up in an actual project, and I'll spare you all the details, but it turned out that there was some sound reasoning behind the fact that the relationship between the unexposed males and unexposed females, keeping it in the language I'm using for this investigation here, gave us parallel lines. And if that assumption of parallelism turned out to be correct, then it turns out that the assessment of the perhaps more crucial issues related to the epidemiology, that is, beta 7 and then perhaps beta 6 and beta 5, which we'll be illustrating later, might be more sensitively analyzed, given that we have correctly used an assumption that really does apply. Now, you might be thinking, wait a minute now, some of those models, they look pretty bizarre. And in fact, I would say that some of them are really pretty strange and would be highly specialized. Maybe the only one that might come up is model 4 in many investigations. But my point for you is just to remind you that the equations that gave us the two lines in the log odds ratio, or the single line in the difference between the two log odds ratios, makes any one of these 8 models at least possible conceptually. Now, it turns out there's other issues that we'll need to address, and I'll mention one of them in a little bit. I'm going to save you that for the moment. But let's now go back to the circumstance of beta 7 being non-zero by means of, say, a statistical test and so on. And we then are faced with, how do we interpret? Well, then it turns out that some of the other regression coefficients come into play here. Some of the other regression coefficients now need to be considered in order to get the description correct. And I hope I can illustrate that for you fairly clearly as we proceed here. So let's take what could be, in some circumstances, the most elaborate of circumstances. That is that beta 7 is not 0, but beta 6 is not 0, beta 5 is not 0, and, for reasons I'll explain in a minute, beta 6 plus beta 7 is not 0. Okay. Well, if you go through basically the circumstances that I've detailed there, it turns out that the odds ratio depends on age for both the males and the females, but the degree of dependency is different between the males and the females. Now, that is our scenario that I have displayed visually for you above. That, in fact, beta 7 is non-zero, large. Beta 6 is non-zero, but you'll recall was negative. And beta 6 plus beta 7 was non-zero, but positive. Okay. Let's now look at some of the other contingencies. Now remember, we've only made one statistical test so far. That is, we've tested the hypothesis that beta 7 is 0, and we have evidence against that null hypothesis. Now we're interpreting the results. We're interpreting. Okay? And it is true that the p-values associated with those other ingredients might be considered in that interpretation, but really the only really important test of significance was that very first one with beta 7. So we're prioritizing, or we're providing a measure of the importance of things. Beta 7 here, very crucial. The other parts important, but that's to enable us to get the descriptions right. Let's take a look at the next example, the next situation, and that is where beta 7 is not 0, but beta 6 is 0. Well, what's that saying? That's saying the odds ratio depends on age for the males, but not for the females. Okay? Because beta 6, in this instance, refers to the line, which is the odds ratio for the women. And let me just remind you what that is. There it is right there. And the slope of that line is beta 6. And if beta 6 is 0, that's saying that the relationship between the log odds ratio and age is not present. But if beta 7 is non-zero, then that means that beta 6 plus beta 7 is non-zero. And so the odds ratio does depend on age for the males, but does not for the females. Okay. Here's what those visuals might look like. There's a possible scenario with the 4 lines, the log odds of disease in the 4 groups, and then the log odds ratio for the men and the women, and then we get a line with positive slope perhaps for the in the reality, but for the men. So here I'm suggesting that if in fact the pattern that we see up above is correct, notice here that the vertical distance is increasing with age for the men, but notice the way I've drawn this, the vertical distance for the women is not changing. There it is for the 30-year-olds, here it is for the 50-year-olds, and the same, because the green line and the blue line are parallel. Okay. So that is a visual description of the fact that the odds ratio is a function of age for the men, but it is not for the women. Notice then we would have a circumstance in which we would say that for the men, age modifies, but for the women, it does not. Another kind of age modification depending on gender. In this case, we see that there is a dependency on age for the men, but there is no dependency on age for the women. And the difference line would be the same because of the fact, the same as the line for the men, because of the fact that the line for the women was horizontal. Now, this is maybe another piece of a terminology that perhaps has not come up yet, and that is that it could be that the odds ratio depends on age for the women, but not for the males. That would be this scenario. Now, you could do that in Stata and explore that, or you could code the men and the women so that G is 0 for the men and G is 1 for the women, so-called reverse coding, and then repeat the analysis. Or you can do statistical tests for sums or linear combinations of regression coefficients. That's also available. Okay. So that's beta 7 non-zero, but beta 6 0. Okay, let's now take a look at the circumstance in which beta 7 is 0, but beta 7 is not 0, but beta 5 is 0. Well, this turns out to be is going to take us a little bit away from the direction that I want to give a lot of emphasis to today. This type of model we're going to be seeing now, where beta 7 is non-zero but beta 5 is 0, is a commonly seen circumstance, but requires very careful consideration. It's most often seen in contexts that are often described as assays or microassays, in that with beta 5 being 0, we're going to get lines in the log odds ratio versus age that emanate from the same point when A is 0. Okay? And we'll see that in a visual in a minute. Now, if in fact we have two lines that emanate from the same point in a graph, that gives us the opportunity to study something called relative potency. Again, we will be coming back to this in a later session. But in fact, it means that we get the ability to study a quantity called the relative potency, which is describing how the explanatory variable works on the outcome. And I'll leave this for your review, but for our discussion here, if in fact this scenario occurs, and beta 7 is not 0, but beta 5 is 0, then we're going to be in a position to be able to say that for the women, they will be Ka years of age to see a log odds ratio that is the same as the men that are A years of age. Oh, that's this idea of relative potency. So the impact of age can be described and in a way that links the men and the women in a way we haven't seen so far. And perhaps a visual will help. Okay. Here is a possible, again, visual to try to help us to understand the circumstances here. Here are the lines in the log odds of disease for the four groups. Hard to make a clear observation here. But what I want you to notice is that when A is 0 here, the difference for the men is the same as the difference for the women. Let's take a look. For the men, it's going to be about minus 0.5 minus 2.5. So that's about 2. Okay. For the women, we're going to get minus 1 minus 3. That is also 2. Okay? Not something that you would maybe have your attention drawn to straight away, but, well, that's the case here. The two lines have the same difference at a equals 0. Wow. That means that when I graph the log odds ratio versus age for the men and for the women, we get two lines that emanate from the same point when the log odds ratio is equal to 2. And now, notice what I have drawn here for you conceptually, and that is that the log odds ratio for the women at age 13 is this value, a bit more than 2.5. But for the men, we get that value of a bit more than 2.5 when they're 5. Aha! K is the ratio of this number, roughly 13, to this number, roughly 5. That's the relative potency in this circumstance. Okay. And then we could also graph, again, the difference between the two log odds ratios. We can notice that it does in fact go through the origin in this particular graph. All these things are in play now. Okay. Now, there is one important issue I want to mention here, and that is models that yield quantities that are specific to an age, when age is measured, need to be viewed with caution. Now, again, this is a substantial issue and one that will be discussed in a future session in more detail. But here it turns out that if in fact we are entertaining a circumstance where beta 7 is not 0, but beta 5 is 0, we're dealing with a model whose fitted values will not stay the same if we center age. The centering of age here changes the fitted values. Now this is, I haven't demonstrated that, and that will be something I will do for you, as I said, in a later session. But it means that you have to be confident that age being equal to 0 means something quite specific, or whatever it is that measured explanatory variable is, when it is set to 0, is something that you do not want to alter. In other words, it would be argued, or you're prepared to argue, that you would not center that variable A. You would not change its relative position. Such a model needs to be used with care. Are you comfortable with the fact here that A equals 0 is something specific? Okay, so I've illustrated visually for you two possible scenarios when we're dealing with a modeling process which begins with the assessment of beta 7, and beta 7 is not 0. And it turns out that I have shown you only two visuals here, and there are many scenarios here, but a sampling of the scenarios that we might see in the real world. But I wanted to point out for you here that if in fact beta 7 is not 0, then we've identified a complicated form of modification. And one can then say that the modeling process stops and interpretation begins. Now, it might be that we might want to be considering possibly one of those other models other than Model 1. Maybe Model 4, possibly others. But but we wouldn't be doing so using tests of significance. I don't believe so. Maybe just to give us qualitative information, perhaps, or preparing some visuals, or possibly conceptualizing some models other than model number 1 there. That is not often seen. Those circumstances, in my experience, are comparatively unusual. But I wanted to emphasize that what we now know is that both age and gender modify when we know that beta 7 is not 0. And what we then know is that age modification is modified by gender and vice versa. So attempting to discuss this particular project with confounding and or simpler forms of modification in this situation simply isn't possible, because any discussion of confounding and or the simpler forms of modification involve assumptions that we've implicitly discredited. Again, the Delury quote, which I think is one of my favorite of all quotations. As a matter of statistical decency, we never average things that differ through more than error. To do so is to distort and deceive. All right. Because now we're going to start talking about the next set of circumstances that we might see in an investigation of this model that began with all 8 terms. So I hope I've given you an indication of the implications and possible interpretations we may face if beta 7 is not 0. What I'd like to do now is continue the exploration of this circumstance, but now we're going to suppose that beta 7 is 0. And that some of the forms of modification we saw up above in those slides have been ruled out. Again, there are various combinations, and I want to look at them for you. Let's begin with perhaps one that might be the simplest. I can't say that with any certainty. But if, in fact, we have that beta 7 is 0, but so is beta 6 and beta 5 is not 0, then notice beta 6 and beta 7 are now removed. And so what have we got? We've got a term that may be telling us about gender as a modifier, right? Because the 2 log odds ratios here, we can see for the men and the women, differ by beta 5. We can see, we can still have gender modification. Okay? Gender modification would be present if this odds ratio, this log odds ratio, is different from this one. That's saying that the odds ratio is different from the men and the women, and that would be an indication of gender modification. Right. So in this instance, we might be considering model 1 here. And since we're considering gender modification, it seems almost crucial then that we would have beta 1 present in all of these models. Again, there may be highly specialized circumstances in which we might want to consider beta 1 is equal to 0, even though beta 5 is not 0. I will not be addressing that here. And again, it is likely that model 1 would be the one that would be most likely in the background here, and not ones with other terms removed. We'll come back to this. Let's take a look at a circumstance. Let's suppose that we have, with model 1 here, we have this scenario here. Okay? What have I drawn here? I've drawn that there is a relationship between the log of odds of disease and age for the women, but it's slight and increasing, but slightly. Similarly, there's a relationship between the log of odds of disease and age for the men, but in this instance, for this illustration, it's declining. But notice here, I'm supposing that the slope of this line for the exposed is the same as the slope of the line for the unexposed among the women. Further, it is the same for the males. Okay? The slope of the red line here, the same slope as the orange line. Okay? What's that saying? It's saying that, well, first of all, let's take a look at it for the women. For the women, we can see that age does not modify because these differences do not depend. The difference between the green and the blue do not depend on age for the women. That says that age does not modify for the women. Okay. Now let's look at the men. The two lines are parallel. What does that mean? That means that the vertical distance is the same. The distance between orange and red is the same at every age. What's that saying? That's saying that for the men, age does not modify, in that the log of the odds ratio does not depend on age for the men. What's that saying? Okay. It means that we have the possibility now that gender modifies. And we're going to rule out or leave out for the moment the fact that and except for the moment that gender does not modify. Okay? Because it doesn't modify for the I think I should have said that age does not modify, right? That age does not modify for the men, and age does not modify for the women. Okay, I think I've got that right. Now, the way I've drawn this vertical arrow is larger than this vertical arrow. This vertical arrow. So the vertical distance for the women is different from the vertical distance for the men. What's that saying? That's saying that gender modifies. Okay? Gender modifies. The difference between the men and the women can be seen in the difference between the log odds ratios. Here, for the women, it's less than it is for the men. Now, the way I've drawn this is it's not a big difference. But nevertheless, let's suppose that visually that's interesting to us. So the log of the odds ratio for the men is higher than the log of the odds ratio for the women. Okay. Now, let's suppose we consider Model 3, this circumstance. So what are we going to be doing here? We're going to be obliging that the lines in age are parallel. If beta 3, considering Model 3 here, If beta 3 is 0, that says that the lines for the women are parallel and the lines for the men are parallel. Let's see if that's the case. Aha! So this is model 3. The way I've drawn this is that if we were to fit model 3, we would see now parallel lines for the men and parallel lines for the women. In fact, all 4 lines now have the same slope. What's that slope? It's beta 2. There it is, right there. The only place age comes into model 3 is in beta 2. And beta 2 is the assumed common slope in all 4 groups. The females exposed, unexposed. Females exposed, unexposed. Males exposed, unexposed. Now, let's suppose that this is the circumstance. We get this difference between the exposed and unexposed for the males, and this difference between the exposed and unexposed for the females. Let's suppose that when we construct model 3, we get the same differences. The information and the visuals are different, but most crucially, the measure of gender modification has not changed. Okay? Here it's this number, and I'm suggesting to you, at least conceptually, that number, that difference, is the same as this one. Now, it doesn't really quite look the way I've drawn it. Maybe it looks bigger. Depends on what you then look at. Okay, are you going to be seeing these differences as bigger or not? Okay. What do we got? Well, if beta 6 is 0, age does not modify. But since beta 5 is not 0, we see that gender modifies. But now what we need to consider is whether or not that capturing of gender modification is because age is confounding. Age might be confounding the gender modification. Now, the way I've drawn this visual is perhaps these two measures, the male-specific log odds ratio assumed common to age is perhaps a bit different from what we got here. It might be, though, that the difference between these two differences is about the same. Okay? That would be suggesting that there is no gender modification. Okay, so I'm giving you quite a bit of information here. This suggests that the consideration of gender modification here, okay, is about beta 4 and beta 5, okay? Typically, most crucially, beta 5. The values of beta 4 and beta 5 need to be considered. And these are the 4 models that might be in play. Probably model 3, the most commonly considered. Okay? But we could in fact have model 4 as well. Notice this model doesn't involve age at all, whereas this model does. So here we're looking at gender modification with a simple adjustment for age, one that assumes parallelism of the 4 lines, whereas model 1 is the more complicated adjustment for age in order to assess gender modification. Okay. Hopefully I've got all that right. So these visuals are behind the equations. I've made the decision here to just look at visuals here for this part of the presentation, along with the population equations, the model equations, rather than setting up a whole lot of other particular illustrations. The models and the regression coefficients one gets are in play here, but here we're really, in a way, what we're doing is we're trying to understand what's going on in the population domain, where these models are being considered as possible for a research investigation. Okay. If in fact we've made the decision that, for example, the difference between the two arrows here is different from the difference between the two arrows here, then we would say there is gender modification. If, on the other hand, we do not see a difference, then we might say, okay, it appears then that we can see, when comparing Model 1 and Model 3, that we could consider gender modification without the consideration of age in this circumstance. But notice I have only looked at Model 1 compared with Model 3. The crude model, or if I may, this is the one-at-a-time model here, the model in which there's no age at all, would also need to be considered. We've already dealt with that in previous sessions. Okay? There's no age relationship here at all. So what's in play? Basically, we wish to look at the characteristics that are involved in gender modification and to what extent they depend on age. Okay? Whether adjustment for age is needed. Here, Model 4 has no adjustment, Model 3 has a very simple form of adjustment, and Model 1 has the most complicated form of adjustment. Model 2 perhaps would be in a much more specialized situation. Again, this particular example takes us back to the microassay scenario that I described earlier. Okay. So I thought I would give you yet another example that might help, and that is maybe where the images are a little bit more clear. I'll see if this helps us. Let's suppose that Model 1, where we've got differing slopes for the males and for the females, but we have parallelism for the exposed and unexposed for the females, and parallelism for the exposed and unexposed for the males. Hence, we can discuss gender modification. So with this image, Model 1 is showing us a big difference. The log odds ratio, adjusted for age, for the males is much bigger than the log odds ratio for the adjusted for age for the women. Okay, let's look at two possibilities then with Model 3. Let's look at, suppose we refit, well, Model 3, and we see the same vertical distance here for the men and the same vertical distance for the women. Well, then that would say that as far as beta 5 is concerned, it doesn't matter whether or not I consider the model that's the most elaborate one or the one that assumes parallelism. Okay? On the other hand, imagine that we have the same circumstance with our data with Model 1, this visual here, and now I'm considering a different set of data, okay? Different scenario. And if we did so, and when we looked at Model 3, we saw no gender modification after adjustment for age. Okay? The adjustment for age here is a circumstance in which we have the adjustment, but the assumption of parallelism between the four lines. Okay? So here we would say we need Model 1. We need the more complicated situation to correctly see that gender modifies. Because if I use Model 3, I do not see gender modification. In other words, this situation is oversimplifying things. It might well be then, the way I've drawn this picture for you here for illustration, is that Model 3 here is actually very close to Model 4. Because what I've drawn here is lines that perhaps are very close to being parallel and horizontal. Okay, these four lines may have zero slope, in which case we're then considering Model 4. This is the so-called crude in this instance, or the one-at-a-time model, which does not consider age at all. Okay? So that's kind of an interesting fabric for things, isn't it? That it could be that we have, with Model 1, we get a clear identification of gender modification, right? A big difference between these two lines for the men and a very tiny difference for the women. Okay. But in Models 3 and Model 4, we get essentially no gender modification. So here, maybe this is a slightly better illustration than the one I showed you first in this particular scenario. But what we've got is a situation in which Model 1 is correctly displaying the gender modification, adjusted for age. And that adjustment for age requires that we adjust with differing slopes for the men and the women. Just to repeat that. Okay, Model 1 has two lines of the same slope for the women and the same slope for the men, but these two lines with the same slope for the men have different slope than they do for the women. Okay. Okay. And as I mentioned, there might be highly specialized circumstances where one needs to consider models with beta 1 equals 0, but again, highly specialized. Same thing with Model 2 there. Probably not one that one would entertain except in highly specialized circumstances. So the real issue then is the study of Model 1 and then Models 3 and 4. Okay. Now let's have a look at another scenario that might be possible for us. And that is that beta 7 is 0 and beta 5 is 0, but beta 6 is not 0. Okay. Now what are we getting? We're going to get a collection of 8 models that all have the log odds ratio being a function of age, and the slope of that line is beta 6. And notice that if beta 6 is non-zero, this is saying that the log odds ratio is a function of age. It depends on age, and hence age modifies. So as we had before, we can then contemplate the different models that might be in play here. All right. What do we got? We've got a this consideration of beta 4 and beta 6 now. And then we've got differing involvement in gender. Okay, how does gender adjust the age modification? Model 1 being the complicated form of it, and models 2, 3, and 4 less complicated. Again, model 3 giving us a parallelism assumption, and model 4 a crude model, if that word crude even applies here. But more again, the model 4 is the so-called one-at-a-time model, where we are not considering gender at all. Here I'm trying to construct the analogy in capturing confounding, that if age modification is seen in model 1 and it is not seen in model 4, that's probably the most obvious comparison. It's adjusted compared with crude. But as I pointed out, models 2 and 3 provide us with intermediate forms for the consideration of adjustment, of adjustment for gender. Okay, let's consider a scenario now. Let's consider a scenario in which we have model 1 giving us this image and model 3 giving us this image. The same circumstances that I detailed for you before are present. Model 3 is going to have an implicit parallelism that we need to understand that model 1 does not have. And then model 4, which I'm not going to have a display for here, would have a much simpler scenario where gender isn't even involved, the so-called one at a time. Okay? Let's look at model 1 here. Now, it isn't entirely clear, but the point being here is that gender does not modify. So what we need to do is conceptualize the impact of age for the men and the women. Okay? Here what we have is an interesting scenario where for the men it's orange minus red, and for the women it's green minus blue. And while it might not be entirely clear here, there is no gender modification in this display. For example, we can see that the capturing of age modification here, say between the 30-year-old males and the 50-year-old males, is the same as that we would have seen had we considered the 30-year-old females compared with the 50-year-old females. So these two lines are the same width, and these two lines are the same width. So the way I've drawn this, the red line and the blue line are the same length, and the same thing here. The blue line and the red line are the same length. Another way to see this is that the pattern of association, in this case the age modification, is merely an adjusted pattern when we try to see how the female pattern looks when compared with the male pattern. And one way to look at this is to just see that I could superimpose this pattern, this green and blue, by merely shifting the orange and the yellow so that it matches, so that if the orange line matches the green line, then that will mean that the red line matches the blue line. Okay? It's a little bit elaborate, but it's not out of the question. It is a possible scenario. It's a circumstance in which gender doesn't modify, but age modifies. Now we're still wondering about whether or not gender might be confounding the age modification. this is the scenario I've drawn for you, and where we have then the pattern of age modification with adjustment for age in its most general form. In other words, we're allowing for a quite general pattern. Model 3, though, is assuming a form of parallelism. Let's look again at what's going on with Model 3. Notice that we're saying that the relationship between the log of odds of disease and age is seen first with beta 2 and beta 6. Okay. In other words, we're going to get, for the females, we're going to get these two lines, and they'll be parallel. Excuse me, what am I? No, it's the male and the it's the male and the female exposed lines that are parallel now, and the male and the female unexposed lines that are parallel. Have a look at the equation. There's stuff to study here. So, this particular situation is giving us a possible scenario where Model 3 yields these fitted values. And it's because of the fact that gender only impacts on this one term, beta 1. Where's beta 1 here? Okay. Beta 1 is the difference between the males and the females. Okay. Doesn't appear anywhere else here. Let's see if that works. Let's see if we can see if this works. The males and the females for... so it's the difference between the males and the females. Let's consider the unexposed first. Males versus females. That is this difference, this little difference here. And it is the same difference, males versus females, for the exposed. Okay. Studying these images is important here. And I hope I've done an okay job of describing them. But I think what I would encourage you again is your own time spent reviewing these pictures and then understanding the implications here. And I hope I haven't muddled it up too much. Okay. But what I would like you to see now is that it is the interpretation of these two that might be in play in determining whether or not we wish to use an adjustment that is elaborate or a simple one. In other words, does any of the adjustments from models 1, 2, or 3 matter when compared with the crude? Or, more crucially, is model 1 giving us something different from model 3? Okay. So there's intermediates here, isn't there? The comparison of adjusted and crude you might think of as involving model 1 and model 4. But the model 3 is a perfectly credible intermediate in the understanding of how gender might confound the age modification. So what we're seeing here is that if at the end of the day we believe we should adopt model 1, that's saying that the correct adjustment for gender requires both the terms beta 1 and beta 3. Okay? Now, if it turns out that the key ingredients here, this almost always involving beta 6, does not change materially, right? These regression coefficients are all more or less the same, even though we're considering different forms of adjustment for gender. If all of these numbers are the same, then Occam's razor would be in play, and we would argue for model 4. Right? We don't need to adjust for gender in this instance. Okay. How about the last circumstance, and that is where beta 7 is 0, but both beta 6 and beta 5 are non-zero. So what have we done so far? We've looked at beta 7 is 0, but beta 5 is non-zero and beta 6 is 0, and the other way around. But we could have a circumstance in which both beta 6 and beta 7, beta 6 and beta 5 are non-zero, even though beta 7 is 0. So we can see that now we're conceptualizing models in which the beta 6 captures the age modification, and beta 5 captures the gender modification. However, it could be that gender modification is seen after adjustment for age, and age modification is seen after adjustment for gender. Okay? And again, we would probably have the model that involves all 7 terms here. All right, this is the situation in which all that's missing is beta 7. But there are indeed here 7 other models that might be involved. The crude, again, would be, I guess, model 8 if I was to have listed them all here. But there, again, is all these intermediate forms. There are all these intermediate forms of how age might adjust the gender modification and how gender might adjust the age modification. Oh boy. Lots of possible scenarios. Now, keeping in mind that one of the clearest comparisons in this situation would be where we compare the one-at-a-time models with the most elaborate. So what we would have here is this model here involving all 7 terms, and these 2 models that involve only adjustment individually. Only accounting for age individually, where this would be the model for the assessment of age modification without any consideration of gender, and similarly this model would be used for assessing gender modification without any assessment or inclusion of age. These are the 2 one-at-a-time models in this instance. However, if beta 5 and beta 6 from the elaborate model are different from beta 5 and beta 6 we get from these 2 one-at-a-time models, then we know we need the more elaborate model. We need the one that involves all the terms. And as I said, there are the intermediate forms of this as well. All right, so what have we done so far in this session? We've looked at modifying a modifier, and we've looked at confounding a modifier. What's left? Well, it turns out what's left is confounding a confounder. And there's considerable amount of language that's used in the epidemiologic literature here. You hear a lot of different terminology. When we have the confounding of a confounder, sometimes authors will speak of joint confounding. Lots of language here. More crucially then, identifying elaborate forms of confounding requires description. In other words, simply saying there's joint confounding requires more information, right? You need to be more detailed in your exploration. You have to offer more. In any case, if in fact we have ruled out all forms of modification, then for the next set of these 8 models, all of them have an odds ratio of beta 4. And our consideration is then, how do age and or gender adjust that value? Our attention is focused on the form and nature of age and gender now as potential confounders. Now here I'm listing the 8 models again that might be under consideration. Here is the most elaborate, where we have different slopes in age. And here is the very simplest, the crude, where there is nothing involving age or gender. Here are the 2 one-at-a-time circumstances, where there is adjustment for age only, and here's the model where we adjust for gender only. And they're intermediates, right, in the comparison between Model 1 and Model 8. Now, there are a whole range of other possible scenarios here. Now, I'm not going to go through too much more of this particular circumstance, but here it turns out that Model 2 and Model 5 involve a crucial interpretation when the variable a, here age, is 0. And this may involve a circumstance in which we have a circumstance in which we cannot center age. We cannot look at an analysis in which age is changed from a centered value of age, because the fitted values would then change. Again, this is more for the future. What is most often seen, though, practically speaking, is authors using Model 1, Model 4, 6, 7, and 8. Now, in fact, Model 4 comes up quite a bit. This is the so-called additive model. Okay? Gender, age, and exposure, all in this model only additively. There's some literature where if you have gender, age, and exposure under investigation, that the authors start and end with Model 4, and that's all they do. That's all that's considered. Now, there might be circumstances, and there certainly are circumstances, in which an investigation based on Model 4 would be fine. But one needs to know that there are implicit assumptions involved in the use of an additive model. Everything in Model 4 requires the terminology assumed common. Let's take a moment for this. So beta 4 captures the log odds ratio, assumed common to age and gender. But now notice that the slope, beta 2, applies to both the men and the women. And the difference, beta 1, applies to all ages and all exposures. So this model requires lots of things assumed to be common. I'll be coming back to the discussion of additive models in a future session. But notice that this is the first time in this session where that model has even appeared. Model 4 assumes there's no modification and a curious form of assumed common to all of the characteristics. So notice the only model with no adjustment is Model 8, the so-called crude in this instance. And Model 1 might still be very important in our understanding. So all 8 models give a value of beta 4. If all 8 models give the same value for beta 4, then that says that neither age nor gender are confounders. Now, it turns out that if one of models 1 through 5 is determined to be appropriate for handling the confounding effects of age and gender, then we've got from this model-based approach something we didn't get from either a one-at-a-time analysis or attempts at stratified analyses. So again, confounding assessment with where we end up with something like what's in models 1 through 5 is something new. Now again, I'll just remind you again, with models 2 and 5, we have something that involves very careful consideration. And as I said, the most common considerations are Model 1, Model 4, and then 6, 7, and 8. 2, 3, and 5 are very specialized. Okay. So Model 1 determines these 4 lines. Right? And what do we got? That beta 4, let's see now, beta 4 from Model 1 is essentially the most crucial here. This is where we have the most complicated of scenarios. All right. So, if beta 4 in Model 1 is different from beta 4 in the other models, and meaningfully different, right? We have all these issues of what do we use to judge whether confounding is present or not, leaving that out of the discussion here. But if we've decided that beta 4 is meaningfully different from Model 1 and from the other models, we can see that to properly control for age and gender as confounders, we need to allow for a different line relating the log odds of disease and age for the men and for the women. We must allow a different slope in age for the men and the women, and a different unexposed intercept for the men and the women. Okay. Now, say, as an example, let us suppose that models 6, 7, and 8 all yield the same estimate of beta 4, but model 1 yields something different. Then we can see that if we'd only considered models 6, 7, and 8, we would have incorrectly concluded that neither age nor gender confound. We can see that adjusting for age correctly identifies gender as a confounder. Symmetrically, adjusting for gender correctly reveals that age is a confounder. So age confounds the gender confounding, and gender confounds the age confounding. So again, as I said, some authors in this literature say that age and gender jointly confound. Joint confounding is a very generic term, and as I said, I would suggest that it more often that you're going to need to describe in more detail what you mean by joint confounding in the circumstance you have. So again, what we have is, I'd like to take a few minutes and refer back to Model 4, the so-called additive model. The additive model here, as I said, in some literature is the only one that's considered, where and sometimes you'll see this language used, we just enter the variables in the model. We enter age, gender, and exposure in the model, okay? That language, or that kind of blurring of concepts, needs a whole lot of discussion too. I can get kind of crabby about these things. I guess I should apologize. However, what we do need to then identify is that if Model 4 is to be used, have we justified its use? Are we aware, are the people using such models, these additive models, aware of the fact that there may be other scenarios in play? An important issue. Okay. So it certainly has a certain ease of use, this additive model. It's just the three terms in the model plus the intercept. But suppose we have a situation in which Model 4 reveals a gender relationship. In other words, that that we get here that that gender needs an adjustment, right? We need to adjust for gender. Here, Model 1 indicates a disease exposure relationship, the blue arrows, while Model 1, where I have assumed parallelism, misses the relationship. Okay. In other words, with Model 1, we get non-zero vertical distances, but with Model 4, we get tiny vertical distances. Okay, so Model 1 then is correctly displaying the disease exposure relationship. And what are we seeing? We're seeing that we really needed Model 1 and not Model 4. Okay. We came up against Model 1, or saw Model 1 and Model 4 when we had just age groups. Just to take you back to that. Model 1 arises in that circumstance, all right, where we have two 2x2 tables for each of the two circumstances. We have two 2x2 tables for the young, and we have two 2x2 tables for the old. We have the four 2x2 tables. Okay. And it turns out that the test for the assessment of joint confounding is analogous to the comparison of models 1, 6, 7, and 8. Okay. Now, Model 4 is not involved in that directly. Model 4 is an intermediate to the assessment situation. That the classical assessment with stratified analysis implicitly involves models 1, 6, 7, and 8. Okay. One more point for you before we close today. Before we close this session, the interaction that's seen in Model 4 here, in Model 1, this term GA here, beta 3 GA, that term that is seen in Model 1 but not seen in Model 4 is for the possible assessment of modification. I'm getting near the end. It's worth noting that the interaction term in Model 1 is not for the assessment of modification. Okay? If models 1 and 4 provide different estimates of beta 4, then Model 1 is to be adopted. And notice the issues here involve confounding, not modification. So I wanted to I hope what I've written is actually clearer than what I've muddled through here in my last remarks for you here. But here's an instance in which an interaction term is used to assess confounding issues. Okay. Okay. Again, we could have done some reverse coding, as I've mentioned, some of the models on that list are very specialized and may not be considered. Okay. Now, notice again that if we only considered models 6, 7, and 8, then we're addressing one-at-a-time assessments, right? Models 6, 7, and 8, here's age only, gender only, and crude. That type of one-at-a-time assessment is sometimes argued as appropriate for the assessment of gender as a confounder and or age as a confounder. And what I hope I have illustrated in this session today is that these one-at-a-time assessments may miss the issue, and that implicit in the use of the one-at-a-time assessments is assumptions that need to be explored.